Problem E2B7 says, what is the direction and magnitude of the electric field vector at the point marked B in figure E2.12 if Q is equal to 11 nanocoulombs and D is equal to 1 centimeter? So our given values are Q is equal to 11 nanocoulombs, which is equal to 11 times 10 to the minus 9 coulombs, and D is equal to 1 centimeter, which is equal to 0.01 meters. So we want to find the magnitude and direction of the electric field vector at B, so at this point right here. So the first thing we're going to do is we are going to use the equation E2-9B. And that says that the electric field is equal to, we're going to use K here. So we're going to say K times Q over, and we're going to use the vector notation here. So we're going to say R cubed times R vector. So that's instead of using the unit vector, which means we have to determine the angles, we're going to use the vector notation here because it's it can be a lot easier to figure out. So the first thing we need to do when we use this approach is we want to find, if we're saying that this is our origin right here. So right at Q2 we know this is 0, 0. We also know that our coordinate system looks like this, right? Where 0, 0 is right here. So if the 0, 0 is right here, then the location of, we'll call this charge Q1. So we're going to say R1 is equal to, and now if I think about the position as a vector, Q1 is located at a negative D, right? That's the x coordinate, from this point would be a negative D. The y would be 0 and z would be 0. Let's talk about R2. So R2, the vector for that, because it's located at the origin, we just have 0, 0, 0. And R3 is a lot like R1, right? Our x position is D, a positive D, and our y position is 0 and 0. So now what we want to do is we want to find, so here we're going to, our R is the magnitude of the distance from our charge to the location where we're interested. And so we're going to call that, we're going to find RB1. And that's going to equal, and that's a vector, so all of these are vectors. So RB1 is going to be, well, let's talk about what RB, let's just say this is just, we'll just call this RB. RB is, it's right above this charge, this Q2 charge, which is at the origin. So we know our x position is 0, and then we know it's in the y direction, it's a positive D, and in the z direction, it's 0. So that's just R, just cross it all out, just RB. And so RB1 is going to equal RB minus R1. So RB is 0, D, 0, minus R1, which is minus D, 0, 0. And so the result of that is going to be 0 minus a negative D will get a positive D. D minus 0 will get a positive D. And in the Z spot we'll get 0. Okay, and so let's just for a minute think about vectors and figure out why that's true. So if I want to do a net displacement diagram, right? So my, let's say this is my origin, and I want to write a vector from my vector from the origin up to B. I'm going to draw this. Okay, and now if I want to draw, so I'm saying RB minus R1. So what that's going to do, I'm going to say minus R1, and that's going to look like this. And that's a minus because, remember, this is the direction of 1, and so we're subtracting. So I need to flip it, right? I would have something that looks like in this direction, but since I flip it, I go that way. And so my vector is going to look like that. Okay, and so this is just the length of the vector, right? It's going to be located here and drawn from here, but we can see that's what it would look like. That is the same net displacement I would get if I just drew that line here. So that's why the mathematical expression is the same as what we could imagine drawing from our net force diagram. So now RB2 is going to equal 0d0 minus 2, which is 0, 0, 0. So I just get what I have for RB, and so that's just 0, d, 0. And now RB3 is going to equal 0, d, 0 minus d, 0, 0. And so I find that that's equal to minus d, d, and 0.